And how did he do this? Well, he got to grips with this really large number, this 6 factorial, and he enumerated every single possible square and showed that none of them work. Now, this is 1900. There's no computers. 36 factorial is a big number. How did he do this? Any guesses?
Lots of free time.
Pardon? Sorry,
Lots of free time.
No, he didn't have that much free time. He was a teacher. He assigned it as homework over years and years and years and years of teaching. He gave out each piece as homework to the students and did it over tons and tons of time. It's astoundingly smart. And it's something that we've come back to in the computer age, right? It's distributed computing. He was doing distributed computing in 1900, right? Like the SETI at Home project, where you get a little bandwidth of the cosmic radiation and you look for signals. He just distributed it out to hundreds and hundreds of computers. And he used the only computers he had, his students. Now, the question, of course, is why people actually care, because it looks like a fun problem and it's neat to do, but that's a lot of time to spend on something which seems mainly recreational. But the truth is that it's actually quite important. These Latin squares are used in the designs of experiments. In fact, one of the first scientifically designed experiments used a Latin square. This was actually before Terry, after Euler, and it was some farmers trying to determine whether you could fatten sheep on root vegetables, because it wasn't known that you could do that. So they designed this experiment using a 4x4 Latin square. They took 4 breeds of sheep and 4 individuals in each breed, and they fed 1 Ile de France potatoes and slaughtered it on the 20th of February, 1 Ile de France and fed it on turnips and slaughtered it on the 20th of March, beets, and then corn, which was more traditional food. And you can see that every breed has been fed on each of the 4 diets, and every breed has been slaughtered on each one of the 4 dates, so you can actually calculate all your covariances and figure out what the best vegetable is and which one works the fastest and allows you to get fatter by March or April or whatever it is that you actually need. And in more contemporary times, they've been used for software network testing. They're used in codes and cryptography. You can show that a perfectly secure code is equivalent to their existing in a certain kind of Latin square. They're used in scheduling, shift scheduling, nurse scheduling, things like that. And something that's not really that important, but they can also be used to build really neat magic squares, which is a nice kind of application. So people looked at this for a reason. Now, I want to change my language just a little bit to talk about the history of the Euler conjecture. So I have my square here. Oh, excuse me. That's not a 5. That should be 4. Sorry. I've got this square, and it's got the numbers and the colors, and I want to actually separate those out. I want to look at them separately to really think of them as that pair. So I pull them apart. There they are, pulled apart. Colors and the numbers. And because mathematicians like to make everything, ugly and drab, I'm going to replace the colors with numbers. So I won't be colorful anymore. So green is 1, pink is 2, 3 is yellow, and 4 is red. And I can reconstruct the colors later, but now I've got all numbers and I'm happy, and I can do all of my kinds of arithmetic and everything. So I've got the 2 squares, and I'm going to make a matrix from them. And it's a matrix that just tells me in row 1 and column 1, what does square A have? A 1. What does square B have? A 1. In row 1 and column 2, what does A have? What does B have? And I made this big chart. And that allows me to go back to the squares, but again, this is something that's a little bit easier to work with, and this is called an orthogonal array, or OA for short, and this one has 4 numbers in it, so it's an OA4. And now I can recast the Euler conjecture by saying an OA does not exist for 2, 6, 10, and so on. And the OA allows me to actually do some things much easier. So for example, only 22 years after Terry, in the new language, McNeish was able to show that if you have an OAN and an OAM, then you can get an OANM. And that's really easy. You just take the symbols from the N and the symbols from the M and you make ordered pairs. How many ordered pairs are there? N times M. And it all totally works out. You just overlay the 2 orthogonal arrays. And Euler knew this, but McNeish also, Euler didn't prove it, but he knew it. McNeish proved that you could find an OAP for any odd prime. So you can do 3 and 5 and 7 and 11 and so on. Well, if I can do all odd primes, and I can multiply any 2 numbers, that's all odd numbers. Because all odd numbers break down into odd primes. So I'm not working on the Euler conjecture, but I'm showing that all of the stuff in the middle does exist. I can do it. And he found an OA4. And that allowed him to do all of these n. 3, 5, 7, 8, 9, 11, 12, 13, 15, 16, 17, 19, 20, 21. He could do everything except exactly what Euler thought he couldn't do. Yes, he needed a 4 to actually be able to do this, and he had 4. So yeah, there's a 4 in here. There. Because you need the 4 to get the, you have to have a 4 and an 8. To get the 12, you multiply the 4 and the 3. And to get the, not the 14, the 16, you multiply the 4 and the 4, and so on. And that was 1922, the way things lay. It looked very good for Euler's conjecture. It was kind of like a mini Fermat's last theorem of its day. It was something Euler said was true, but never in his life managed to prove, and people were working on it. But in 1960, Bose, Shirkahande, and Parker, some statisticians, showed that in fact 2 and 6 were the only ones that couldn't be done. You could do 10, and you could do 14, you could do 18, and so on. And they had a very nice construction where they built a 10. So here it is without the colors, right? So my blue numbers my black numbers used to be my colors, and you can check that you get every blue number once in each row and column, and you get every black number once in each row and column. And there's a black general, and where would be another general? 9 general, etc. And they did it, and they showed the constructive all. And this was 1960. So another 40 years after McNeish, looked like he put the conjecture on solid ground. It was broken. Well, at the same time, in 1960, there was a group of French writers and French mathematicians who were getting together, and they called themselves the Oulipo, which was the Ouvroir de la littérature potentielle, and they published a manifesto and saying that the aim of their group was to invent or reinvent restrictions of a formal nature and propose them to enthusiasts interested in composing literature. And they themselves were the principal enthusiasts who did the composing of the literature, but many people sort of joined them. And I want to give an example of what they actually meant by this restrictions of a formal nature. You can think of it as kind of playing games with literature.